That's my desktop. I forgot to start the timer, so I just started now. So I'll be a little bit late. Sorry. Okay, cool. So Titanic. Who has seen the movie? Come on. Who has liked the movie? Come on. In their youth, I mean. Anyway, we know Titanic's about, it's a love story, right? There's a ship, the ship sinks, a lot of people die. Yep, it's really good, it's really good. So I happen to have here a folder with some files here. And there's like surprise sh, that's the script I use to do like image to ASCII. But there is a file which is called train CSV. And this file contains some actual historical data of the passengers of the Titanic. So you can see there's a passenger ID, there's survived, which means they survived or not. The passenger class, the name, the sex, the age, the number of siblings or spouses, the number of parent or children, which ticket they had, how much they paid for the ticket, which was their cabin, where they embarked. So what I'm planning to do today is to basically investigate if the movie had any sort of like historical truth to it or not. And that's my only goal, actually, when I started the project. So yeah, whatever. So we're going to use some really cool Python libraries to do that. And I'm not really a Python guy. I'm not a data science guy. So like the general, like, I think thing is, if I can do it, anybody can do it. I just can copy some code off the internet, get it to run, understand like the basics of it, try to change it a little bit, and then, I mean, like if I can do it, like, anybody can do it. So I'm just gonna write, I'm going to write a lot of code in this presentation. Hopefully I'm not gonna mess it up like too badly. Probably I will. So let's start. Visualize.py. So we're going to import this library, which is called pandas. It's an amazing library, and you should like take a look at it. And using pandas, there is a way of like loading a CSV directly, and they call it a data frame. So I'm going to call it a DF. And if I do pd read CSV, and I'm going to pass train.csv, I'm going to have this object which I can print the shape, and I can print some count, right? And if I save this, I run it in Python, it'll say, okay, we have 891 rows, 12 columns. And then the count, we can see that for every one of those columns, we can see which rows had that information. So we can see that in this case, for example, we didn't have age for some of those, we didn't have the cabin for some of those, we missed some embarked. But like in general, like the data looks pretty good. So what are we going to do first is to take a look at the data, because it's pretty useless to try to run some machine learning algorithm on some data you have literally no idea what it is about. So, and it's also pretty fun because you get to create some cool graphs. So there's that to it. Okay, so let's try to do something with it. So I'm going to import a library which is called matplotlib and has a little function called pyplot as plt. I'm going to create a figure with plt.figure fig. You have to pass the fig sides. I'm just going to pass something like this. And now I'm going to delete this. I'm going to show something at the end of it. And now I'm going to do df survived value counts. And now matplotlib adds this amazing plot. And you just do kind bar. And I'm going to pass an alpha just because otherwise it's a bit too painful on the eye. So if I run this, something appeared on the back. And you can see this is actually the survived column on those 900 rows. 0 means unfortunately deceased, and 1 means survived. And we can see it's like more or less 350 survived, 550 died, right? But our human brains aren't really so good at reading raw numbers, so I want to use some like percentages. And luckily it's quite easy. You just do normalize true, save, run again. And now you'll see, actually this is like something I can reason about. 40% of the people survived and 60% of the people died. It would be interesting to take a look, since we have the information of like all the age of the passengers, to take a look at what relationship there is between the age and the survival rate, basically, right? So the library provides a really nice function, which is called scatter. And if I just do scatter, I can pass def survived, def age. And in this case, I'm going to pass a lower value of alpha because a lot of dots are gonna like end up on each other. Let me also add some title to these things. So survived, and this will be survived. No, actually be like age with regards to survived. And in this case, actually, if we ran this code right now, it would like display all the like graphs like on top of each other, and we don't want that. So instead, we're going to use this function which is called subplot to grid. And you can just pass like these general dimensions of your rectangle, and then like this is the spot this graph will take. So I'm just gonna put like this first and this second. And if I run this, you'll see you have this really nice looking graph. If we take a look at this, it's pretty interesting because we can see that 0 still means deceased and 1 means that, survived, sorry. And we can see that it is true that like some of the older people died, and instead some of the younger people survived more. But actually, like the bulk of all the dots are pretty much in the same range. They're between the 20s and the 40s, and there's no like huge, like change in the data. At least like it doesn't show, right? So I thought just like it's really, really interesting. As soon as you get this like raw CSV of stuff, like you can't really figure out, just like to try to cut it through like some sort of dimensions and take a look around. And like maybe there's something in it. Okay, cool. So something else I'm gonna do is just like take a look at the passengers class distribution. So I'm just gonna do some like quick copy paste. Instead of survived, I'm going to do p class, and here this will be class. Python. Yep. Almost. And we can see that 55% of the people were in third class, so like that was like the poorest class, and 25% of the people were in first class, and the rest were in second class. So there's like a pretty uneven distribution of the passengers in those classes. Now, there's something pretty cool that you can use when you want to correlate two different dimensions. So basically, one of these is the scatter plot. Another one is called a kernel density estimation. I won't bore you with what it means, but it really looks cool, so I'm gonna build one for you. And basically, I want to correlate the class with the age of the passengers, right? So I'm gonna, and also like this has like a nice, little thing. So I'm sure I'm going to trigger some PTSD around the room because I'm going to write something which looks like this. Call span. Yes. No web developers using tables. No one wants to admit it, right? So call span 2. So this graph will take 2 columns. I'm just going to do for 1 in, 1, 2, 3, and then do df h. And in this way, I'm filtering, like what I want to extract is the age of my passenger, but between the square brackets, I can filter stuff. So in this case, I'm gonna filter their passenger class, just do something like this. And then I'm just gonna do plot kind equals KDE, which stands for kernel density estimation. And now I can just give it the title. So this would be basically their class or th. And just for your safety, I'm going to add a legend to it. So it's just first class, second class, third class. Okay. And this looks pretty cool. What does it mean? If you take a look at the average of the ages, the third class passengers are younger. And instead, the first class passengers are older. It's sort of like there was some sort of relationship with how much money people had with the type of tickets they could buy. And I think it's just like some good ways of trying to make sense of information, just like try to visualize it a little bit. And as you can see, it's really simple to do these graphs using matplotlib. I don't know what I don't know if I had to do this using D3.js, I'd probably just like gave up the project. No offense. So I'm just gonna add one last image to this, which is just to show where the passenger embarked on the Titanic. So here I'm just gonna do here and here embarked. And this is like very useless information, but I think it's funny because I never knew this myself. And actually, I thought that everyone just like got on in England, but actually only 70% of them got on in Southampton. And then the Titanic stopped once in France in Cherbourg, and then it stopped again in Ireland, in Queenstown. So like this like set of information shows also like where these passengers are coming from. And probably the data could also tell us there is some sort of relationship between like where they got on the Titanic and if they died or not, which is creepy. But if you take a look at this, I think this is really cool. I'm just gonna screenshot it. I think it's, yes. And if you take a look at these graphs, there's something missing, which is the gender, right? There's like no like cutout on the gender of the people who were on the Titanic. And the reason why I did that is because the gender is really interesting. So I'm just gonna do some simple copy paste. I'm gonna copy this. I'm going to create a new file, which is called visualize gender, pi, new, almost, yeah. And here, I'm going just to keep the same structure. I'm gonna add a couple more graphs, so I'm gonna make like the rectangle bigger. And here I have something like this. And actually in this case, I want to drill down a little bit. So I want to check if the sex of these passengers were male, and just do this. And here I'll just do men survived, and copy this again, and just change this to female. And this would be woman survived. Cool. So here, 1, 2. Just a small little detail, I'm going to change the color of the grass for the girls. So it's going to be FA0000. No, that's cool. And here I'm going to do color equal female color. Okay? And I have to show the graph again. So PLT show. And if I do this, they look quite good. I mean, unless you realize that actually in the case of the women's graph, the columns are inverted. So actually of all the men, 20% survived, and of all women, 70% survived. So when they say like women and children first, was actually quite true. And if we wanted to see just like the disparity of the like the sex comparison, like in all the survived people, we could do that quite easily, just like in the exact same way. So we just like copy this little thing, and we are just gonna set it like on the last cell. We're going to we want to show the sex now, but now we want this filter to act on the survived column. We're gonna do 1. And here we're gonna do sex of survived. And I'm going to add like 2 colors in this graph so we can like differentiate between them. So this should work. And you see like this is the difference, right? Like of all the people who survived the Titanic, at least like on this data set that we have, I think this data set has only 1,000 like passengers, and in total, like in the Titanic there was like 3,000. But I think it's like a pretty good way, just like, you know, like looking at things like in a sort of like almost objective way. And you see that like of all the people who survived, 75% of them were women. Now I'm going to do something really similar to what we did before, which is kernel density estimation. I'm going to try to use the class of the passenger to show their survival rate. Okay, let me close this. Let me know if I'm going too fast or if there's like something which is boring. So what do we do before? So like the same thing, using call span again. So this is like on the second row, starts from the 0, call span equal 4. And here we can just like do some good old copy pasta from here, yay, and paste here. Cool. And what we want to show here is not the age anymore, is the survived, right? And here would be survive, no, would be actually class with regards to survived. Okay. So, and there we have it. So this quite it's quite scary in a sort of way, because you see that the third class passengers had such a higher mortality compared to the rest. And instead, you see the first class passengers. So it's not the best holiday they had, but it's pretty good. So this made me think, well, what about if you try to combine this information about the sex and the passenger class together, and try to show that on all the different spots. If you remember the movie, there's this guy who is very poor, and he's a man, and this girl who's very young and very rich, right? So we're just gonna see if the movie holds on this core criteria. So what we're going to do is to just copy some code. I'm just going to do a lot of copying of code, basically my daily job. So there's some colleagues as well. So oops. So 0, and here I'm going to add 2 filters together. So I'm going to select people which are male and df class equals 1. So we're selecting the rich man. Rich man. Hope it's not derogatory in any way. P3, and this would be poor man, and I'm going to put it one close to each other, right? Yep, there it goes. So we can see that actually, in the poor, in the rich man, they're not doing great, but they have 35% survival rate, and instead the poor men are doing horribly. They have basically a little over 10% survival rate. So what if we try to replicate this experiment with the women? So we'll revert to some good old copy paste again. Here, copy paste here. You either have some code prepared or you have to copy paste. So no shame here. Female. And here will be rich woman, and here would be poor woman. Okay, and also here I'm going to let me just convert this. Okay, color equal female underscore color, and I'm going to do the same thing here. Okay, and I think upgraded the columns as well, so I'm just going to run this. Cool. So yeah, this is pretty brutal, right? You can see basically the rich man had a survival rate of 100%. If you print out the actual data, there's 100 rich women, and only 3 of them died. If you take a look at the poor women, they're not doing, they're doing okay, but they're still 50-50. And if you take a look at these graphs, it's pretty clear why, this is Jack, and this is Rose. So, right? Okay, so I spent a lot of time just, showing data and doing stuff like that. So I hope, it's time well spent. I'm going now to use some algorithms to try to, predict this data. So the first algorithm I'm going to use is very simple. Well, the simplest algorithm would just be random, and you have more or less 50% chance of getting the right answer, because it's either survived or deceased. But taking a look at this data, one could think of a very simple, heuristics, right? It would be, if you're a woman, you survive. If you're a man, you die. I'm sorry for the audience, because, this case would be pretty brutal. So I'm just gonna exit from here and create a new file, which I'll call predict gender, pi. And here I'm going to import pandas again as PD. Here I'm going to give a name as train, because in machine learning there's a lot about the training set and test set. So I think it's good just to call it train instead of df, which is a panda specific term. So I'm just going to do read CSV train.csv. And inside here, as you've seen before, we have everything. We have all the columns. You can filter through them. And what is cool is that you can actually add more stuff. So you can do, I can add a new column, which I call hypothesis. And in this, I'm just going to fill every row to 0. And then I'm going to use a method which is called lock, which you pass a condition and the column to update. So the condition would be if the sex of is female, and the column I want to update is the hypothesis, I'm going to set 1. So this is like pretty simple. It means if the passenger I'm like taking a look at is a female, I'm just gonna like my hypothesis she's gonna survive, right? And now we just need like a simple way to check if our hypothesis is correct. So oops, can't type. And just do lock again, and here would be if the survived column is the same as our hypothesis. Okay, I'm going to update the result column with 1. Okay, and now I can do print train result dot value counts. Right? So like, I think this like makes sense in a sort of way. You think, okay, like here's my hypothesis. If she's a girl, she's going to survive. And then I'm going to compare my hypothesis with the actual recorded value, which is the answer, which is survived. So if I do this, did I save? I hope so. No, the F is not defined. Oh, well, I just said I'm going to call it train. So I'm going to replace the F with train. And done. And now it says 701 is like we know like 1 is good, right? Like 1 means that our hypothesis is like the same answer as the survived column. But as I said, as humans, we can't really read these numbers. So I'm gonna play the same old trick, which is normalize true. And you see, wow, 78%. It's like such a simple heuristic, but it gives us like a 28% increase on just a random algorithm. So I think this is like a really good reason why you should always take a look at the data first before running any algorithm on it. Because sometimes just like a very simple, hint could give you some like really good answers. And you will see, in the future that the more complex algorithms we run, they won't give us like such a massive increase anymore. Because like there isn't like that much more truth in the data anymore. Okay, but I think this is pretty cool. So I said I was going to write a lot of code, but actually I lied because there is some code I didn't want to write just in front of you because it's like boring as hell. But I'm going to explain like what it doch. So there's a function which is called clean data. We pass some data. It fills all the rows which don't have the fair information and will like fill them in with the average value. They do the same with the age. They're going to transform the sex from a string to a number. And this is because a lot of these machine learning algorithms are nothing but basically number crunching algorithms. So they don't really do well with the categories that like our human brain deals with, but they're really good with trying to optimize numbers. And that's why you usually always want to do this sort of normalization and transform these things that we know mean something into just like pure numbers, in this case, integers. And so I'm going to do the same with like male. So like 0 will mean male and 1 will mean female. And I'm going to transform also the embarked information as well. Okay. So I think now I've learned something from Nusco before, so I'm going to cheat as well. There's like this, I love the web. So let's try, yeah, look at that, how beautiful it is. So, yeah, so this is just, like some graph. We have some leaves here, we're just like data points. And if I were to ask you, what is the general trend of these data, you'd say, well, it's like something like this, right? You're like, yeah, like more or less like everything is there. And like the simplest machine learning algorithm just does this. It's like, it's no magic. It's just like takes a look at the data points, tries to run some sort of like number crunching algorithm on it to try to understand what is a good line that fits the data. And it tries to minimize the error between what he thinks the value should be and the actual value. So like the first time you see a machine learning algorithm run, you're like, yeah, whatever, like this is dumb. I could do it, right? The problem is like we're really good as humans to do this on 2 dimensions. But if I were to ask you to do the same operation in 15 dimensions, yeah, right? Like I can ask you, time zones. Who understands time zones? Raise their hand. Really? Phone numbers? Who understands like phone numbers? You know, standards. It's really, really hard. Like if you try like to read the source code of a library who like tries to do that for a job, you're like, whoa, this is so hard. Like I can't keep all these like things in my head. I think the same happens with like different dimensions. They're just like too much stuff. Like our brain is just, it's just like struggling a lot. And this is the reason why like a good numeric approach beats the human brain, because like we're not really good at like dealing with 20 dimensions. If you think about like image recognition tasks, they usually assign a different dimension to each pixel. So you have an image which is 50 by 50 pixels. You're trying to solve a problem which has 2,500 dimensions. Like who can do that? I don't know. I can't. I can't like. I have like some issues like with this, to be honest. So I'm going to create a file which is called predict logistic regression pi, and I'm going to import. Actually, maybe I can just like copy some stuff. I mean, we're copying anyway. So what do you call predict gender? I'm just going to. Well, actually, there's nothing could copy. That's dumb. But I'm going to use my utils, which I just explained before. And then I'm going to use this extremely good Python library, which is called scikit-learn. So scikit-learn implements a bunch of machine learning algorithms. Just basically, you don't have to do anything. And what I've shown here, this is usually called, like in machine learning terms, as a linear model. And it's pretty clear to see why. It's just like trying to get like a very simple explanation of the data. And from scikit, this is like no surprise linear. You just import linear model, right? Cool. So here I've like imported our CSV. I'm going to use the utils to clean the data. So I'm just going to do train, right? And here I'm going to have to do a couple of things. So I have to pass this algorithm what is the desired output, which is usually called target. And it's quite easy to do this. You just do survived and do values. And then we have to pass a set of information which are called features, which are basically what we tell the machine algorithms that like, these are the hints. You have to figure out stuff. Like we're like really kind of like, you know, like the cousin, which is sort of like berates people. Like, oh yeah, just like get this and do it. I don't really care like how you do it. So the way we're gonna do that, we're just gonna pass like some information like the passenger class, like this, the age, the sex. I mean, we can pass, you know, like the number of sibling and spouses, the parent and children. I think that's enough. And just pass these values. Values, cool. And now we're going to create this object which is called a classifier. And it's called a classifier because it just needs to take one of these passengers and decide like which one of these buckets like he needs to assign it to. So I'm just gonna call it a classifier, and we just take linear model, logistic regression. Yes, cool. And we just do classifier fit. We pass the features, we pass the target, and actually maybe we want to assign this to like another variable. So I'm just gonna do something like this. And now we can print like the results of this classifier. So basically, as soon as I set fit, the classifier tries to go through every row of the data and tries to find like some hidden relationships in the data. And then just as a way of like basically double checking if the thing is like doing anything at all, we can use like this score, and we pass the features and the target again, and this thing will print out like the accuracy. From import, right? I don't know Python. I said it. Cool. And you see, it says like 0.79%. So like it's 79%, which is better than our like naive interpretation. And I'm sure that like if we add like some more information, let's say the fare and like where they embarked, probably the algorithm will do better. See? Basically, we're just like telling him, okay, like you have like all these things to work with. Just like find me a good explanation of this. And I go back to some drawings because like when you see something like this, I think it's pretty clear for us, okay, like this is the trend, right? But if we try to fit the same line like through here, like our human brain is like, oh, wait a second, like this doesn't look right. You know, like the data is like showing like a different behavior. And like this is usually known as a quadratic behavior. So like we as humans, we would say, oh, it's basically something like this, right? It's a curve. And I don't want to trigger PTSD again, but like in math, it's called like a polynomial. So usually it's like a first degree polynomial, it's a straight line. If it's a second degree polynomial, it's like more of a curve, and then you go crazier and crazier. So no PTSD, please. But like there is something in scikit-learn which help you to do this, and it's called pre-processing. And what we can do is to take our linear features and transform and combine them into second-degree polynomials. So basically, it's a way to say, okay, maybe our data could be described better with these curves instead of straight lines. So I'm just going to need to instantiate this. I think it's something called polynomial features. They're pretty good with names. Degree 2. And here I'm going to create some polynomial features. And I'm going to do poly.fit transform and pass the original features that we had. Okay? And here, basically, we can just like do the same thing again. We're going to do, actually, we don't need to change the classifier because we didn't override it, right? So I'm just going to separate it a little bit. And I'm going to print this thing out on the polynomial features. Poly features, and the same thing here. And you see, like using the polynomial features, that was like a pretty big win. So we started, but like as I said before, like it's not like really that much of a win, like considering like what's like our simple like human intention, like intuition got us to, right? So I thought like this is like, yeah, okay. I mean, computers work pretty well, but like we humans like don't suck that much. Unfortunately, there is like something which I haven't said. Because like when you see like code like this, you're like, wow, this is like really, really easy, right? So like what's the trick? Like why is like your neighbor like not doing machine learning for fun? And the reason is a lot of these algorithms are a lot like black boxes, so you don't really get to understand too much what's happening in them. So I'm going to show an example, and then I'm going to show some tools that we can use to try to prevent these biases of the machine. Every time I say biases of the machine, it seems like some like dark, you know, like sci-fi future. So let me just do something which is extract this into feature names. I'm going to call this feature names, and then paste this. Okay, cool. And now I'm going to copy this into a new thing, which we'll call predict decision tree. Paste. Here we won't need the preprocessing, we'll just need the module called tree. And basically what this algorithm does is to create a very simple decision tree. So we'll take a look at the data at every row, we'll take a look at like all the characteristics of it, and we'll try to build some sort of like decision tree, like a literal decision tree. So we'll start, this is like the biggest decision that like moves me or nudges me in a certain direction or not. And as you'll see, like for me, it's like really simple. I'm just gonna do decision tree equals tree. I forgot the name of it. Decision tree classifier. Decision tree classifier. And here you have to pass something which is called random state 1, just because in this way you initialize the decision tree with some random values. And something which happens a lot in machine learning, because if you start a decision tree with 0, these optimization algorithms are going to struggle a lot, because they're doing, well, derivatives. I didn't want to say that, but they're doing derivatives to try to improve the situation. So if you start with 0, they have like basically no direction where to go to. And instead, if you start with random numbers, they'll like nudge a little bit like into the right direction instead. But for me, as a user of the library, this like makes no difference whatsoever. So I'm just going to do decision tree underscore equals decision tree dot fit, and we have the features and we have the names, right? And here I'm going to do print decision tree underscore score features names. No, names not defined. It's called target. and the same here. And it's 97%. That's really good, right? Unfortunately not. Well, I wish it would be like so good. But basically, the reason why this thing like thinks he almost got it right is because machines are quite ruthless, as we know. And if you just give machine free rein, he'll just like try to do like the dumbest thing possible, which means that it will try to fit a very basic, like the intuition of it will try to fit a very high order polynomial to it. So you will see something like this, and it'll try to fit a curve like this. And we're like, what? This makes no sense, right? But the thing is, since like most of these methods are numerical, they don't really, you know, like they don't have like our sense of judgment. So they're just trying to fit as much as they can. And then since we trained this like classifier on all the training data, it's always going to do, okay, I'm just trying to like, you know, do my best. And it's going to come up with like really weird results like this. So of course, they tried to come up with a lot of techniques to try to limit this, to try to fix this. And one of the ways is basically play hide and seek with the algorithm. So you're just gonna intentionally withdraw some information. So I have these 10 points, but I'm only going to pass the algorithm 6 points, because I know that the algorithm otherwise is going to get like overzealous and it's going to try to read too much into the data. But what I want the algorithm to do is to try to keep like a sort of like generalization, right? And this would be like quite hard to do it yourself, but of course there is an amazing model, like a module in scikit-learn, which is called model selection. And I mean, I think it's like the general like, gist of the talk is just like learn scikit-learn because it's amazing. And yeah, but if you take this thing and there's a function which is called model selection dot cross val score, which is called a cross-validation score. So as I said before, when you're withdrawing information from the algorithm, like in machine learning terms, the part of data that you're not using, well, it's not completely true, but whatever, just like bear with me. The part of data you're hiding from the algorithm, like its general name is cross-validation set. It's not always true, but bear with me. And so here you pass the decision tree, you pass the features, you pass the target. You have to decide like a scoring like algorithm for the thing. In this case, we're going to use accuracy, and then you specify basically how many times he has to do this operation, right? And now we're going to print the scores, and we're going to print the average of the scores as well. And remember, this is something where we had 98% like accuracy before. But if we hide stuff from the algorithm actually reveals that as like, yeah, almost, right? You see, like the average of like these 50 runs was like 0.78%, which is not super bad, but it's basically just as good as like the super simple approach that like my cat probably could like come up with. I have a picture of my cat here. Oh. I used this like another case. It's not like, yeah. Anyway, so like a good way to try to fix this is to try to basically tell the algorithm, well, try not to read too much into the data. So here there's like, when you're creating this classifier, you can specify some information, which is a max depth. So basically you won't try to create a tree which is deeper than 7 like levels. And then you can control also the sample split. So it's basically when he decides that he has to branch out. And in this case, I'm just going to say 2. And also in this case, I'm going to replace decision underscore with how do you spell it? Generalized? Yeah. And it's 1, 2, 3, 4, 5. This looks good. So if I run this, you'll see that like our like generalized version of the tree was like way less confident on the first run. It said like 88%, which was like still higher than the average when we tried to hide data from him. But like, in general, it was like gave like a much better performance than the like over-optimistic one, right? And one of the huge problems in machine learning is that it's really hard to understand what the machine is thinking. And luckily, there's some really good tools, especially in decision trees, which will allow to visualize this information. So I have to remember the correct API, but it's something like tree, export graph viz, and you pass our generalized tree underscore. You pass these feature names so that he can like associate with something, and we say out file equal tree dot, and it's a dot file, right? So if I run this, it worked. I'm gonna switch to, I'm gonna try to switch to another shell. Oh, I was in the shell. Okay, that's cool. And we see there's a tree dot. It's here. And if we take a look at this, is tree dot, whoa, it's like not for humans still. But like since it's a dot file, there's this amazing tool just called dot. And you can transform a dot into something which we can process with our brains, which is a PNG. And if I open that, you'll see this is what the algorithm sees. I'm going to zoom in if I can. Cool. So do you remember like what was like our simple heuristic? Is the sex. And in the process of cleaning up the data, we set sex to 0 if you're a male or 1 if you're a female. And you see that the tree makes that like the top decision. So the decision tree understood that the sex is like something really, really important. And you see that it like splits off the samples. So like we have 891 here, but then if you're a man, we have 577 samples here, while on the other branch we only have 314. And then the immediate decision after that is, what is your age? If you're a kid, you have to go on this side, and there's only 24 deceased people here. And instead here there's like 500, well it's not deceased, but there's like only a subset. So the maximum like deceased people in this set could be 24, and here in the other hand side it would be 543. So in a sort of way, the algorithm understood like the human notion of women and children first, right? And it's here, it's not like a joke, right? It's like he actually built this, and it's an algorithm who did this, like just like by looking at the data. Cool. How much? I don't have much time. I think that would be it. Just a small thing. So I've put like most of this code on my GitHub. There's a repo which is called Jack Dice. Yeah. So there's also like all the instructions to set it up like on macOS, but I think like the same thing just works on Ubuntu or whatever you're using. I'm going to live tweet this technology. So here is the repo of no slides conf. Good. No slides. Cool, and that'll be it. There's also more algorithms on the repo because I couldn't fit all the material in here. So for example, something which I think is super cool is that they have this thing which is called a grid search, because like most of these algorithms have a lot of parameters that you can fiddle with. And so they came up with this little thing which just like dumb, like in a really dumb way, will just like try out all these different algorithms with like different parameters and just figure out which is the value which works best. I think in this specific example, it doesn't really work that well because you only have, like 900 rows. But like in a real case example, you'd have, 20,000 rows or 40,000 rows. So if you Google, billions of rows. And actually, like these things like work much better. So I think like you don't, like even if you do that yourself, like don't get too, stuck into, oh my God, this algorithm isn't working, because machine learning, like I think a paper came out 5 years ago which just said your algorithm doesn't really matter that much. Like who has the most data wins. So yeah, questions. Come on. I think someone said I'm not gonna leave, like let you guys leave if you're not asking questions. So it's a standoff. Yeah, one there. That's how like you get to leave the room.
Okay, as a developer, I think a lot of people is like me here. We don't know where to start to do this stuff.
Yeah.
And because I tried with Coursera, other stuff like that, but they are too too theoretical.
Yeah.
That's and we have another kind of approach. It's fine, but where we can start to do this stuff.
So I did the Coursera, like the machine learning course on Coursera. It has a little bit of math, but I think that the teacher on that course is really good because it says, okay, this is the math, but it doesn't matter. As long as you understand the intuition between like some of the machine learning concepts, that's fine. And it's just like, you just search for Coursera machine learning. I really recommend this course. And this is the guy who actually created Coursera, like this guy. He's like the CTO of Coursera. And this is really, really good. But something I have to admit is I stole a lot of stuff for this talk from this amazing website, which is called Kaggle.com. It's a data science competition website. So they do real stuff as well. So if you go on competitions, you'll see some of the top competitions have, you know, $150,000 prize, right? It's called Kaggle.com. And some of the, like this Titanic is one of the challenges. And for example, this is like where you get the data. They just like expose the CSVs. And there's also, you can make a submission. So they also give you a test set where they don't give you the answer. So you have to train your machine learning algorithm and fight against each other. That would be the idea. But then the internet came along and people, you know, like started to figure out the real historical data so that their algorithm would get 100% success rate. So you see, like the top submitters are like cheating a lot, and this is not actually what like data science is supposed to be. But anyway, like that's the end of the rant. But if you go here, there's like some really, really good Python notebooks. So if you take a look at, I think it's here. So it's easy, like you can use Python, you can use R, and they have like really, really good explanations about everything. So what I did at the time is just like go through, you know, like 10 of them, and just like take a look at what are the best techniques and the things which I found more interesting. Like something I'm really, really interested in personally is neural networks. But I think, like for example, on this problem specifically, it's not a good fit for a neural network. So like you don't see like many people using it, and if they do, the performance is not great. If you want to play with neural networks, there's another really sort of like classic problem, which is the handwritten recognition task. And that's really cool, because like you get to write a program which reads something like this and actually assigns it like the correct class. And it's like it's like sort of the hello world of data science. And it was only invented 15 years ago by Yann LeCun, which is now head of the Facebook AI group. But it's like a very, very classical task. It's just like so satisfying when you write the neural network and you see that it's actually recognizing handwritten digits, especially since you are a developer, so you know how you would solve it otherwise, right? You think about the digits, you think about the shapes they are, you try to run some stupid like image conversion algorithms or like some algorithm to try to rotate the number in the right position. Like you have like this way of thinking, and instead the neural network just applies this sort of like brute force to it. And it's just like, there you go. This is like the result. And I think the like the industry standards for this problem, now they have 99.8% accuracy, and human beings have something like 98. So in some things, like these things are already unbeatable, and they have been unbeatable for the past 15 years. So. But it's really fun, so I really recommend it. They have a lot of like examples in code there, so if you want to learn, it's really good.
So how do you decide which algorithm to use? Do you just throw all the algorithms at the problem and look at the numbers, or are there any heuristics?
Yeah, that's the hard question, because basically, I mean, from what I've seen, I'm not an expert whatsoever, but from what I've seen, the people who are expert will just tell you, well, over time you'll learn which algorithm works best with what problem. So a lot of these competitions on Kaggle, for example, I haven't seen like good applications of neural networks, and I'm kind of pissed at that, because I really want to see like how like one of these like real world problems can be solved using machine learning. But like there are some really good papers about like how like you use like neural networks in image recognition, stuff like that. So I think there's a sort of like general feeling in the community, which are the best algorithms like which solve like some sort of problem. And every year they like publish like a crap load of papers like trying to prove that their algorithm works the best. But I think already like 5 years ago, they sort of came up with the idea that the best algorithm doesn't really matter that much. So they did like this really like serious experiment where they just like ran, like 10 different algorithms, and they changed how much data they had. And they saw that when like they had a lot of data, like all the algorithms would pretty much like converge to the same point of performance. So it's mostly like how much you can afford, like what is like your, machine learning architecture. But they see like most people care just about like how much raw data you have. And I think like since I learned this, I'm much more understanding of like why Facebook, why Google are so interested in your data, because like that's the real valuable stuff, right? Like a lot of like data set that we have just like to play around are like 1,000, 2,000, 3,000 data sets, like rows. And I'm sure that the internal data set that Google engineers have to train their algorithms is just incredible. Right? And that's like the real value of it. And that's why their machine learning algorithms work so much better than the rest. Well, they're really smart, but they have also a lot of data.
Okay.
Is it good? No more questions?
Okay.
Cool.
Thank you. Thank you very much.